everyone. How are you doing? All are doing good? All are doing great? That's great, my boy. That's great, my girl. That's good. Keep it up. I'm Mahesh, your physics teacher, and you're watching me right now on SMR Online Physics. If you're new to this channel, do not forget to like, share, and subscribe my channel for many more interesting video classes on the topics of physics. Hope I'll be greatly helpful for your physics classes. Alright, so let's get started. Right now this is my lecture 3 on the topic of refraction of light. So let's get started with refraction of light by a glass prism. This is what we are about to discuss in today's class. In the previous class, I discussed about the refraction of light by rectangular glass lamp. If you haven't watched it, do watch it and then come back to this video. Great? Okay, let's get started. Now, do you have any idea what is a glass prism or how does it look like? I hope so. You have seen it in your school labs. If not, right now I can show you a 3D diagram how a glass prism exactly looks like. Historically, it's an important tool because one of the greatest scientists ever, Isaac Newton, used it to discover something more fundamental about the light coming from the sun, right? So a glass prism basically has two triangular cross section, and I will try to draw it in a three-dimensional way so that you get a right picture. This is how it looks like. It has triangular cross section as well as rectangular surfaces, and this is how it looks like. Absolutely perfect. So let me call this as PQR. Alright, so here you'll see that, my dear, it has two triangular cross section, PQR front and exactly the back surface, two triangular faces, and then you see this 1, 2 and 3. There are 3 rectangular surfaces. So a prism in total has 5 surfaces, 2 triangular, 3 rectangular. The rectangular refracting surfaces are inclined at a certain angle, and that angle between these two surfaces is denoted by capital A, called as angle of the prism. Alright? So in today's class we'll get to see what happens or how does a ray of light behave when it comes from air medium, strikes upon one of the rectangular refracting surfaces, and how does it refract out of it. That's why I told you, to understand and get a good feeling how does it behave, first of all get a feeling of rectangular glass lamp. Alright, so how does the ray of light actually refract in this case? Alright, so let me rub this off. And now for diagrammatic purpose, I'll be drawing only a triangular cross-sectional surface, okay? Imagining this is an equilateral prism, this is how it will look like. Does it look good? Yeah, nice. This is what I call as the angle of the prism A. Alright. So now let us name the surfaces P, Q, R. So if a ray of light is incident obliquely on one of the refracting faces of the prism, so you need to understand that the ray of light is coming in from air medium into something optically denser medium. So let us say that it's made up of one good quality glass. Again, after passing through the glass medium, it has to go back to the air medium. That's it. So air, glass, air. Something very similar to the glass lamp part. Okay. Now my dear, observe this, how to draw the normal. Yes, normal should be always drawn perpendicular to the interface. That's good. So this ray of light is actually in this direction, but we all know that it doesn't go in that direction. And that is what we call as refraction. There's a change in the direction of propagation of light. Now it's moving from optically rarer to optically denser. So it is going to bend towards the normal. So let me show you something like this. Alright? So now again the ray of light has to pass from the second interface or the second refracting surface, glass to air. So this would have been its original straight path direction, but it won't go that way. That's clearly visible. So let me draw one more normal at the point of incidence. Normals are always drawn perpendicular surface. Now denser to rarer, yeah, it should be bending away from the normal. That's it. That's as simple as that. Rarer to denser, denser to rarer. So the ray of light has actually gone in that way, then it refracts, then it refracts out. This is how the refraction looks like. So let me give you some names. L, M, N, and let us call it as O. Alright? So here, my dear, L, M, the ray will be called appropriately as the incident ray of light. That's good. Mn is called as the refracted ray of light. And NO, which finally comes out of the glass prism, NO should be called as the emergent ray of light. So when you have three rays, naturally you have the angles also coming up. So I can mark it directly in the diagram. This is your angle of incidence, I. The angle formed over here, this is called your angle of refraction. But there is another angle forming over here, so we call it this as R1, the other one as R2. And finally, the ray emerges out of it. So this angle is called angle E, the angle of emergence. Now my dear, it's very clearly visible that the ray of light came in this particular direction. So instead of going straight, it has bent this much away. So it has deviated away from its intended path. How much is the total angle of deviation? To know that, just produce this emergent ray backwards and meet the original direction of the incident ray. So the angle created between the incident ray produced forward and the emergent ray produced backward is the angle of deviation. So I mark it here. This is your angle of deviation. That's it. So we can find an expression for how much is that angle of deviation and on what factors that angle of deviation actually depends upon. Alright? Come on, note it down. Let us find an expression for this angle of deviation. Alright? All in terms of angle of I, angle of refractions and angle of emergence. So let me quickly rub this off because we will be requiring some good space to get to that beautiful expression which will show you on what factors the angle of deviation in fact depends upon. Alright, so you see that, my dear, now you focus, okay? Focus very strongly. This ray of light, instead of going straighter, has bent along this path. So this is the deviation. The first ray suffers at the first interface. So let us call this as delta 1, the first angle of deviation. Then this ray of light going straight should have gone through straight, which I show by dotted lines. Doesn't go that way, but actually bends out. So this has to be your angle of deviation. This, or you say this, has to be exactly your angle of deviation, delta 2. Sorry, this angle, right. This angle or this angle. That has to be a delta 2. Alright. So that's your angle of deviation clear. Is that clear? Is that clear on the board? Hope so, right. So here we can see from geometry that if you look into this, let me mark this very important point over there. Let us call it as B. So if you observe this triangle of BMN, we have this delta 1, delta 2, this is the exterior angle. So from the figure, we have delta, the angle of deviation is equals to delta 1 plus delta 2. That's good from geometry. All right. Now, if you observe these angles, if you observe now, angle I can be written as equal to, focus here, R1 plus delta 1. So from this, I can easily find out delta 1 should be equal to I minus R1. That's good. Correct? Similarly, angle of emergence E should be equal to delta 2 plus R2. So delta 2 should be equal to E minus R2. Agree? Agree, my dear? You can pause it and cross check it perfectly. That's great. So now we can substitute these values of delta 1s and delta 2s in this equation to find an expression for delta. Alright. Hence, in equation 1, we will find delta is equals to I minus R1 plus E minus R2. So here we go. So delta should be equal to I plus E minus R1 plus R2. This is one good expression, but we can make it much more better. So I would like to still call it as my expression number 2. I plus A minus R1 plus R2. Do we know what is this R1 plus R2 equal to? Yes, we can definitely find it. Okay? Right. So what should be the angle of delta is equal to if I get an expression for R1 plus R2? So I'm going to rub this off the top half quickly. Right. So let us quickly see that what we have. Simple geometry, my dear, very simple geometry. Look into this normals connected to each other. You can even call this a C. So in the triangle MCN, I find that R1 plus R2 plus angle C should be equal to 180 degrees. That's good. Correct. But at the same time, if you see this on the larger picture, this is also a quadrilateral, you find it there, okay? So in the quadrilateral, what is the name of the quadrilateral? PMCN. We can write the angle of the prism plus angle M plus angle C plus angle N should be equal to 360 degrees. So from here, I easily find out that this is your angle A, this is your 90 degrees, this is your angle C, this is another 90 degrees. Please check it out. M and N making an angle of 90 degrees because there is a normal connected with the surface. So hence we find an expression angle A plus C is equals to 360 minus 180. We are left with 180. Now observe this and this. The right hand sides are showing to be equal to 180. So left hand sides can be equated to be equal to 180. So from these two expressions, therefore, R1 plus R2 plus angle C should be equal to angle A plus angle C. That's great. And we lose this angle C. Hence, very, very important, the angle of the prism is always equal to R1 plus R2. Super important. That's it. Very important. You see that? Now we can put it there. So hence we can say, is visible, right? The angle of deviation is equals to I plus E minus the angle of the prism. this is your priced equation. This is the priced equation. Clearly visible. Delta, the angle of deviation, is equals to I plus E. So it definitely depends upon the angle of incidence and also depends upon the angle of the prism. Alright? Come on. Graph for the angle of deviation for various angles of incidence, we will obtain a very unique graph. So let me get rid of these equations. I'm sure that you have noted them down. Okay, that's it. Alright. So keeping that diagram on the side, let me draw a graph over here. If I plot it on a graph, this is my x, this is my y. I'm going to plot over here the angles of deviation, alright, and the various angles of incidence over here. Alright, come on. So you'll find that experimentally the plot looks something like this. The plot obtained will be something like that. Okay. So here you can see that for any particular angle of incidence, there is a unique value for angle of deviation. But this angle of deviation also is produced for a different angle of incidence too. If I say I1, this is I2. Yeah, I1 and I2 is not same. But for the same I1s and I2s, you have the same angle of deviation. But there is a unique point in this entire curve, somewhere here, that for angle of incidence, for this particular angle of incidence, the deviation suffered by the ray of light is found to be the minimum, and we mark it as the angle of minimum deviation. This is the one, and this is obtained for a unique angle of incidence. Alright, so when it is exactly possible, let us see. Just now we obtained an expression delta is equals to I plus E minus A. So for unique I, there will be unique E also. So if I becomes equal to E, if I becomes equal to E, then you can see in the expression you will get 2I minus A. So then this delta is called as delta minimum. This is the expression for the minimum angle of deviation. The minimum angle of deviation is equals to twice of angle of incidence minus the angle of the prism. So practically drawing, physically, you will find that it is true for a unique angle of incidence, and the ray of light which has strike upon the surface here, instead of going straighter, now the refracted ray will be observed to be parallel to the base of the prism, and then you draw another normal, it bends away, right? So this angle of deviation, what I find over here, this is called as the delta minimum, the minimum angle of deviation. So physically I will be equal to E. This is a very, very unique condition where the refracted ray will be observed to be parallel to the base of the prism. So from this expression I can also find out I is equals to delta minimum plus A by 2. This is an expression for calculating the angle of incidence, right? To E for the minimum angle of deviation, so it is also clear that this R1 should be also equal to R2. So on this condition, R1 is also equal to R2, geometrically correct. So if this is true, therefore we will have A is equal to R1 plus R2, and both are equal to each other. So from here I can write A is equals to 2R, or R can be written as A by 2. So if you know this angle of incidence and if you know this angle of refraction for the minimum angle of deviation, it also helps us to calculate the refractive index of the material of the prism. So the ray of light is coming from medium 1, let us say is going from refractive index N1 into refractive index N2. Hence, my dear, therefore we can say N2 by N1 should be equal to sin I by sin R. Clearly visible? Right. So I can write N21, yeah, so is equals to sin, what is that I? Yeah, this is the value we could easily put in there, delta minimum plus A by 2 sin of R, which can be happily written as sin A by 2. So practically we can easily measure, I mean to say experimentally, the delta minimum is measurable and also the angle of prism is measurable. So if you know these two from your practical observations, it becomes very easy to calculate the refractive index of the material of the prism. Hope I'm clear? Feeling good? Feeling happy? Give a like. Come on. So we are here. We are in a very good position to learn about this entire thing. So we are going to end up the thing right now. So we got this expression, N21 is equals to sin delta minimum plus A by 2 by sin A by 2. For very thin glass prisms, okay, for very thin glass prisms, you will find that angle of deviation is very small. If the prism is very thin enough, the angle of deviation is very small enough, then we can say this expression, the sine of delta minimum plus A by 2 to be almost equivalent to delta minimum plus A by 2, and the expression sine A by 2 can be almost equivalent to A by 2 only for very thin glass prisms. So if I put that in the expression, therefore you will see that N21 can be written as delta minimum plus A by 2 by A by 2. So the 2 gets cancelled out, so you are left with N21 is equals to delta minimum plus A by A, or you can see that we can easily find out delta minimum is equals to N21 into A minus A, or you could have written delta minimum is equals to A common N21 minus 1. So this expression clearly illustrates that the angle of deviation for very thin glass prisms is highly negligible. It depends upon the angle of the prism, and this is refractive index of the material of the prism minus that 1. Alright, hope I am very clear on this topic of refraction of light by a glass prism. If you have liked my video, if my video was helpful in understanding you, in making you understand the concept I mean to say, then definitely a like to banta hi hai. Do share it among your circle of friends and subscribe my channel SMR Online Physics. So always our motto should be high on the mind. Physics has to be always fun to learn. So my dear students, stay healthy, stay fit, stay safe. See you again in my next class. Okay? Bye.